Welcome to this Masterclass Explainer. Today, we're tackling something absolutely fascinating based on the foundational work of Dr. Nima Mahadian. We're going to take the invisible, deeply complex physics of thermodynamics and make them, well, completely visible. And more importantly, entirely controllable through applied mathematics. If you've ever wondered how engineers tame the chaotic heat of massive industrial furnaces or perfectly balance the temperature of a mixing tank, you are in exactly the right place. Let's get right into it.
Our goal today is pretty ambitious, but I promise it's incredibly rewarding. We are essentially building an analytical engine together. We'll start with the fundamental physical laws, the raw abstract reality of heat, and then we'll translate them step by step into concrete engineering control using Laplace transfer functions. We're going to derive the equations, examine the block diagrams, and unpack the exact mechanisms used in real-world industrial thermal processes.
Here's our roadmap for the explainer. We'll kick things off with the fundamentals of thermodynamics, then explore the three heat transfer pillars. After that, we'll apply it all to controlling industrial fluid mixing, before tackling linearization and control loops. Finally, we'll look at regulating room ambient temperature and wrap up with the limits of analytical modeling. Moving logically like this is going to make sure you're totally prepared when we hit the advanced transfer functions later.
All right, Section 1, Fundamentals of Thermodynamics. Okay, let's dive into this. Before we can even think about controlling heat, we need a mathematical framework to understand how it behaves, right? So we're going to translate these somewhat abstract thermal concepts into a system you probably already understand intuitively.
Take a look at the familiar electrical circuit here on the right. Believe it or not, we can use this exact same logic to understand the thermal system on the left. It's like a universal language. In this framework, temperature acts just like electrical potential, or voltage. The flow of heat, that corresponds perfectly to electrical current. And just as a resistor restricts electrical current, thermal resistance restricts heat flow. This is given by the equation where thermal resistance, RT, equals 1 over K, which is simply the change in temperature, divided by heat flow, Q. Now look closely at that bottom equation for thermal capacitance, CT. It's the integral of heat flow over time divided by the change in temperature. Basically, it represents the system's ability to store heat energy, much like an electrical capacitor stores charge. Just to firmly anchor this dense visual math we just went over, let's quickly reinforce these exact analogs. Temperature is our voltage, heat flow is our current, thermal resistance is our electrical resistance. Seriously, keep this comparative framework in your mind. It's basically the Rosetta Stone that's going to allow you to read complex thermodynamic equations as if they were simple circuit diagrams. Moving on to Section 2, the three heat transfer pillars. Now that we've got our mathematical translation key, let's bring it back to the physical reality of thermodynamics. We need to look at the actual mechanisms that physically move this heat energy from point A to point B. And this brilliantly illustrates exactly how thermal energy migrates in the real world. On the left, we've got conduction, which happens within solid materials. Right in the center is convection, which is driven by the movement of fluids, so liquids or gases. And over on the right, radiation, where energy actually traverses empty space via electromagnetic waves. This is a dominant force when you're dealing with extreme high temperatures. Let's briefly solidify these foundational definitions. We want to make sure everyone has the conceptual tools ready before we jump into the heavy derivations. So, conduction transfers heat through solid, continuous materials, driven by microscopic molecular vibration. Convection transfers heat through the bulk movement of fluids themselves. And radiation? That transfers energy via electromagnetic waves, and it doesn't even require a physical medium to travel through, which is pretty wild when you think about it. All right, let's break down the conduction formula. Look at this cylinder. The heat flow, Q, travels from the higher temperature, theta 1, to the lower temperature, theta 2. The thermal conductivity factor, capital K, equals lowercase k times the cross-sectional area A, all divided by the length L. The crucial takeaway here is how physical dimensions literally dictate thermal resistance. If you increase the surface area, A, you reduce the temperature difference needed to drive that heat flow. But conversely, if you increase the length, L, you increase the required temperature difference. Now, let's contrast the fairly straightforward linear convection model with the highly complex radiation model. For convection, shown on the left, the conductivity K is linearly proportional to the convection coefficient H and area A. Easy enough. But look at the radiation model on the right.
It's incredible, right? The heat flow Q is proportional to the fourth power of the temperature difference. Because of this massive fourth power, radiation exhibits highly complex, nonlinear dynamics. To handle this mathematically without going crazy, we often have to linearize the relationship around a specific operating point, usually by using graphical, slope-based resistance approximations, just for small temperature variations.
Section 3. Controlling industrial fluid mixing. With our fundamental physics and heat transfer mechanisms firmly established, let's shift gears from pure theory to our first 3D microcosm application. We're taking these math equations and dropping them right into the real industrial world. To transfer thermal energy into a cold substance, modern industry relies on several primary mechanisms. You'll notice the four main industrial architectures right here: mixing hot and cold fluids, heat exchange between solids, liquids, and gases, chemical combustion, and electrical heating. Applying our thermodynamic laws allows us to build precise mathematical models for these highly critical industrial setups.
Let's zoom in on fluid mixing. Imagine we have two fluids with different temperatures, theta 1 and theta 2, and different flow rates, F1 and F2. They're entering a tank, and our goal is to achieve a perfectly uniform outlet temperature, theta. We generally have two control strategies here. Strategy 1, on the left, regulates just the cold liquid flow, F1, to manage the final mix temperature. Strategy 2, on the right, is a bit more complex. It controls the ratio of hot and cold fluids, so F2 over F1, while perfectly maintaining a constant total output flow, F. To actually model this mixing tank mathematically, we have to rely on the first law of thermodynamics, energy balance. The total heat flow is the specific heat, gamma, times the density, rho, times the flow rate, F, times the temperature, theta. The fundamental rule is always this: energy in minus energy out directly equals the change in stored energy. So looking at the equation at the bottom, the energy from stream 1 plus the energy from stream 2 minus the energy exiting the tank directly equals the rate of temperature change inside the tank. That's expressed as gamma times rho times volume V multiplied by the derivative of temperature with respect to time, d theta over dt. Take a second to let that sink in.
All right, section 4, linearization and control loops. Here is where we face the primary conflict of this explainer: non-linear reality. The world of thermodynamics is messy, it's chaotic, and it's highly nonlinear. But our standard control systems, they require clean, linear equations to function. So we have to introduce a mathematical tool to tame this complexity.
Let's see how we build this linear model. We linearize by looking at steady-state perturbations. First, we define a steady-state condition where flows and temperatures are perfectly constant. Those are marked with an asterisk. Then we introduce small deviations, defined by the delta symbol. For example, this small delta theta, that's the tiny fluctuation in our tank's temperature away from its steady state. By substituting these perturbed variables into our energy balance and subtracting out the steady state equation, we isolate the dynamics of just those tiny changes. And that yields the standard form rearrangement at the bottom. It's a beautiful, linearized differential equation that we can actually use.
Now we guide this newly linearized equation straight into the Laplace domain. We let K1 and K2 represent our input coefficients and define a time constant T equal to volume over steady-state flow. Taking the Laplace transform gives us the algebraic equation you see in the top right. Assuming a constant total flow where the change in F1 and F2 basically cancel out, we arrive at our final transfer function. The change in output temperature over the change in input flow equals K over Ts plus 1. And there we have it. Just look at the block diagram. Physics has been successfully translated into a highly practical control loop. Now a controller can monitor the error, adjust the flow, and seamlessly maintain our desired temperature. Moving on to Section 5, regulating room ambient temperature. Let's transition to a new application and apply these advanced Laplace concepts to a macrocosm we all instinctively understand: heating a standard room. Take a look at this system architecture. Just think about the thermostat in your own home. A radiator supplies a controllable heat flow, Qi, to the room. The room's interior temperature is theta, and it constantly loses heat, Qo, to the ambient outside temperature, theta A. The room walls possess a specific thermal resistance, RT, and the sheer volume of air inside possesses a thermal capacity, CT. It's a classic everyday balance of heat in versus heat out. Now, what's really interesting about this slide is how elegantly the math synthesizes the physical reality. Our thermodynamics equation simply states that heat in, Qi, minus heat out, Qo,
equals the thermal capacity CT times the rate of temperature change, d theta over dt. The output heat flow, or the thermal loss, is simply the temperature difference between inside and outside, divided by the wall's thermal resistance, RT. By substituting that heat loss equation right into the dynamic energy balance, we create the core differential equation that governs exactly how the room's temperature responds over time to both your radiator and the freezing weather outside.
Translating that differential equation into the Laplace domain yields this architecture. Walk through the block diagram with me here. The controller compares the desired temperature against the actual room temperature to generate a heat command, QI. This heat flows into the room's thermal resistance and capacitance matrix. But notice the ambient temperature, theta A. It enters the summing junction as a totally uncontrollable system disturbance. The controller's entire objective is to continuously adjust the radiator's output to combat that ambient disturbance and flawlessly regulate the internal room heat.
And finally, Section 6, the limits of analytical modeling. We've seen the immense power of translating physical laws into mathematical control models, but we must now transition into the final paradigm shift of this explainer. It's time to acknowledge the horizon and, frankly, the ultimate bottleneck of our analytical toolkit. Up to this point, we have successfully modeled mixing tanks and room radiators by translating fundamental physical laws into mathematical state equations, leveraging linearization and transfer functions, but there is a massive analytical bottleneck. Creating complete, exact analytical models for massive industrial systems with numerous, disparate, interacting components, it becomes overwhelmingly complex and functionally restrictive. The equations simply become too massive to solve practically in real time. This demands a major pivot from purely theoretical modeling to experimental, data-driven methodologies, which is known as empirical system identification. Let's cleanly synthesize the entire workflow we've mastered today. We start with fundamental physical laws. Then we write the differential state equations. We tame the messy nonlinearities through linearization. We map it all into algebraic control loops using the Laplace transform. And finally, when the systems become just incredibly complex, we move to empirical identification, which leaves us with a pretty provocative question to end on. As our industrial systems grow exponentially more complex, and if analytical math truly has a hard bottleneck, will empirical, data-driven models eventually replace fundamental physics entirely in the control rooms of tomorrow? Definitely something to think about. Thank you so much for joining this Masterclass Explainer.